So hi, my name is Stephanie. I'm a PhD student at UCLA, and today I want to talk about solving signaling ambiguity through cooperation. Closer? Okay. So how can humans convey really rich ideas using sparse and often ambiguous signals? Well, the answer to this is context. And here I'm going to focus particularly on two types of context. The first comes from what you can say. So under cooperative communication, we can think of it as a way to change other people's beliefs. And from this standpoint, I should interpret your signal as being the most straightforward thing you could have possibly said. So here you can see, while the signal purple can literally mean either the purple square or circle, the pragmatic interpretation of this would be that it's the purple circle. Otherwise, you would have said square, right? And the other type of context I want to focus on is based on what you can do outside of language itself, right? And even young toddlers are very sensitive to this fact. So here in this particular experiment, the toddler is able to differentially interpret an ambiguous request for help based on the capabilities of the experimenter. Either her hands are occupied or they're free. And this toddler will more often choose the far item when her hands are free than when they're occupied, operating on under this cooperative logic or sort of joint utility reasoning, that if it had been like the near item, she would have gone for it herself instead of asking for help. And so while these two strategies have been studied separately, they've rarely been combined in the same task. And that's what we're actually going to do here. We combine them in the same paradigm. And this is actually important for like Bayesian theory of mind-based modeling, as both beliefs and actions are an important part of the inferential process. And in order to extend this modeling into the communication domain, we also want to see how people and humans are behaving in these situations. So what we're asking here is essentially, do actions speak louder than words? How do people use their beliefs and their actions to solve ambiguous signaling? And what happens when these two strategies give you different answers? So we've designed this paradigm, which is essentially a signaling game, but put in a grid world visual like spatial environment, where the goal here is to reach this target item in the fewest number of steps. However, only the like signaler knows which item is the true target, and they can send a message to their partner, who's going to be played by the human participant. And that message is like a single feature of an item. So gameplay works like this. The signaler who knows the true goal can either walk to that goal themselves, or they can send a signal. And in reality, this is pre-programmed. However, the participant doesn't necessarily know this. So once they choose their action, maybe they say purple and the receiver hears purple, they can decide what they want to do. And they can hover their cursor over different items to see the relative number of steps that it takes each agent to get there. And then once they make a selection, they click on their item and they walk to that item. So here we have two experiments, and the first one contains 4 conditions. We have a baseline, as well as testing both belief-driven and action-driven strategies separately, as well as in conflict. And then in the next experiment, we test a subset of these conditions. And we measure as outcomes which item people select, how long it takes them to make that decision, as well as how confident they rate themselves about that decision. So the first condition we have is just to establish like a baseline that the signaler is being cooperative. And they're just going to walk to an item themselves when it's jointly efficient for them to do so. The second condition is this belief-driven pragmatic reasoning, where you can't actually use utility to help you solve this. So while purple can literally map onto either the circle or the square, the pragmatic response is the circle. But both of the consistent items are equidistant from the participant, and all items are closer to the participant than the receiver. The third condition we have is action-driven utility reasoning, right? Where now pragmatics can't help you to solve this because the two items are identical. So purple can map onto both triangles equally, and you have to use the utility dynamics to solve this. So one item, the purple triangle at 4, 2, is closer to the participant than the other one. However, at the same time, it's also closer to the signaler. So if you're reasoning under this joint utility, you should actually choose the purple triangle at 0, 5 instead. And then the last condition we have is these two heuristics or these two strategies start to come into conflict. So from a pragmatic reasoning standpoint, you would actually choose the purple triangle. However, at the same time, this is jointly inefficient, right? And if you were using joint utility to solve this, you'd reason, oh, the signaler should have gotten that purple triangle. Instead, it must be the purple square. Okay, so we looked at individual participant strategies, and on the x-axis, you have each participant who took this. There were about 50. And then on the y-axis, we have the split by the different conditions, and we'll look at the distribution of their strategies. So what we actually find in the pragmatic condition is that there is this general overall population preference for pragmatics, but we're not seeing that overall population preference in either the utility condition or the conflict condition. However, what we do see in the conflict condition is that people are very highly internally consistent about their strategy. So like over 3/4 of people choose a strategy and they stick to it. And not only that, we see that their decisions in the utility condition are highly correlated with their decisions in this conflict condition. So if they were using joint utility in the utility condition, they're likely also using it to solve this conflict condition. In terms of decision time and confidence, in the utility decision, we see people are more confident when they're making these joint utility decisions, but it takes them about the same time. However, for the pragmatic condition, what we see is that people are slower to make pragmatic decisions, but more confident about them. And this really checks out with a lot of the modeling work underlying this phenomena, right? Where pragmatic reasoning is built on top of literal reasoning. And then in the conflict condition, what we're actually seeing is that people are both faster as well as more confident about their joint utility decisions. And so we wanted to investigate this a little bit more and sort of confirm the effects of this joint utility reasoning that we're seeing. And this is why we ran a follow-up. And this follow-up removes the individual pragmatic and utility conditions and just has this conflict condition. And the reason for this is we were thinking, well, it's possible that those other two conditions could bias people towards learning a strategy that maybe they wouldn't have come up with on their own. And what we actually see in this case is that without those two conditions, there is like now an overall preference for joint utility reasoning over pragmatic reasoning in the population. And we also see that individuals are still highly internally consistent. About 2/3 of them choose a strategy and stick to it. In addition, we can replicate the other behavioral patterns from experiment 1, where people are both faster and more confident about their joint utility decisions. So in conclusion, we've essentially found that both beliefs and actions are used to disambiguate ambiguous signals. And when forced to choose, people are very highly consistent about their strategies. And moreover, they're faster, more confident, and in our follow-up, they prefer this joint utility heuristic over pragmatics. So in the future, what we'd really like to do is, instead of making the signaler pre-programmed, have this as some kind of live interaction with role reversals to sort of enforce stronger cooperative norms. And additionally, here we tested these two metrics in conflict, but we'd like to see them in conjunction to try and replicate some of my previous simulated effects. So with that, I'd like to thank everyone here, as well as my PI, Tao Gao, and 2 of my undergraduate research assistants who have worked with me on this, Sophie and Max.
Unfortunately, we won't have time for the contributor talks, so we'll just go to the next one. So next one we have towards human agent communication via the information bottleneck principle, presented by Mika.
Thank you. My name is Mikal Tucker. It's like call me, but Mikal. And I'm excited to share some work titled Towards Human Agent Communication via the Information Bottleneck Principle. This whole talk is going to be about communication. And so I want to describe some of the principles that we think describe good communication. And the running example I'll use will be communicating about color. Let's say I see a color and I want to tell you about it. A good communication mechanism by which to share this information should be highly informative. Let's say I have some belief over a color, I talk to you, you recreate that belief in your mind. We want to maximize the mutual information between these distributions, my belief and your belief, and that can be characterized as informativeness. So good communication should be highly informative. At the same time, communication should probably have bounded complexity. Here I've shown about 330 colors, but most people don't talk about colors with 330 unique words. And so we probably want to bound complexity or the mutual information between beliefs and communication signals. Maybe I'm going to say red, green, blue instead of crimson, fuchsia, color number 320. And then lastly, in many tasks, we care about task utility. So if we're driving in streets, it's really important to be able to distinguish between red, green, and yellow, as opposed to different shades of red. And so we might say communication is good insofar as it enables high utility, which is a function of the state and actions one takes. And people have, of course, already studied these terms in communication a lot. I don't want to claim I'm the first one doing that. Many people in studying human communication focus on complexity and informativeness. So Noga Zaslavsky, the senior author on this paper, among others, has studied the information bottleneck framework of how humans communicate about colors. So for the very same colors I just showed you, they gathered human data on how over 100 different languages name these colors. And you can measure the complexity or informativeness of these languages in the color domain and plot them as a function of complexity and informativeness. And there's a maximum theoretical informativeness for a given complexity. You can't convey more information than your language allows. But many languages lie near this optimal limit, and different languages exhibit different complexity levels. And so this manifests itself, for example, as some languages like English using about maybe 10 to 12 words, other languages using far fewer words. And it's all just a trade-off of some parameter beta, which is how much do you care about complexity versus informativeness. So people have studied this in human languages in color domains and in so many others. So typically people study informativeness and complexity of human languages, while in emergent communication domains, the typical emphasis is on utility. We train agents to play some task well and communicate to enable high mean reward. In our framework, perhaps unsurprisingly, we say, well, we actually want to combine these three terms. Let's maximize a weighted combination of utility, informativeness, and complexity. Here we express informativeness as negative distortion, but they're equivalent values. And this framework, I apologize for that formatting. This framework allows us some intuitive interpretations of the effects of these terms. Complexity makes communication range from silence to highly complex systems that are uninterpretable to people. Informativeness ranges from communication that describes everything in a scene to nothing at all. And task utility makes it a task-specific jargon or something that is task agnostic. And we can train agents in a neural architecture to trade off these terms. We hypothesized in our experiments that when we trained agents and penalized complexity, that penalization of complexity in particular would be critical in inducing human-like emergent communication with no supervised data of how humans communicated. We trained agents using a variety of emergent communication architectures in a color reference game. So using the very same colors I showed, we drew one color at random, gave it to a speaker agent corrected by some noise. The speaker communicated to a listener who observed the original target color and a distractor color and had to say which one it thought was real. And we could slot in, as I said, different neural architectures. We proposed a novel architecture dubbed vector quantized variational information bottleneck. I'm happy to elaborate on details at my poster. Intuitively, it samples a point in a continuous space and then discretizes it to one of a discrete or finite set of communication vectors. We could measure the emergent communications informativeness and complexity just as others have studied human languages and plot them, again, relative to a theoretical curve of maximum informativeness for a given complexity. These two curves for one-hot-based communication and our method are essentially on top of each other. If you zoom in, our method actually achieves slightly higher utility, but we show that we can train agents to achieve high informativeness for a given complexity, and we can vary complexity by just changing the single weight of how much do we penalize or reward complexity. For example, for a specific weight penalizing complexity, we don't penalize complexity that much, we can visualize a 2D principal component analysis of communication. Agents learned to communicate here seemingly with about 7 clusters, right? There's a word for yellow, a word for orange, a word for green, etc. We can visualize what that looks like in the color space. And then because we have data of how humans communicate, we can compare to human languages, shown in dashed lines. And so a more complex emergent communication system can look like this. But then using that very same system and just saying penalize complexity a little more, communication evolves and clusters merge, right? Instead of yellow and orange, we get a single word for yellow-orange. We get a simpler, less complex communication map, and it lines up almost perfectly with a different human language that, again, is less complex. I think when I saw this, I was really excited because we essentially recreated a human-like communication system with no human data. And of course, we've done experiments in other domains, multi-agent reinforcement learning settings, et cetera. And we also studied attributes of emergent communication using our method. Again, I'm happy to elaborate upon them later. The thing I want to leave you with, though, is our framework, which emphasizes the trade-off of these 3 terms in training emergent communication: informativeness, complexity, and utility. Our novel architecture better supports trade-offs between these. But then more importantly, beyond emergent communication specifically, what's exciting about this work, we're not the first to claim this, but it is yet another data point for how training AI systems with notions from cognitive science can induce human-like behavior that better aligns with our expectations. Thank you. That's it for me.
Thank you. Okay, so next we'll have our first lightning talk presented by Tan Xuan. So the title is Solving the Baby Intuition Benchmark with a Hierarchy Bayesian Theorem Mind. I think she's going to be virtual.
Yeah, hi, can people see me okay? Or hear me okay at least? I guess I'm not
Yeah,
sure.
we can see you. We can.
I'm not at least for showing up in the
Oh,
spotlight.
no. Yeah, no.
Cool. Great. So good to see everyone here. And my name is Shan. I'm here to tell you a bit about a poster later called on solving the baby intuition's benchmark with the hierarchically Bayesian theory of mind. So baby intuition's benchmark is a recently published suite of tasks by Gandhi, Stoynik, Lake, and Dillon, designed to test the ability of computational models to judge the plausibility of agent behavior in accordance with infant psychological intuitions. For example, infants expect agents to act efficiently or exhibit preferences over goals. And if we want to build socially intelligent machines, we probably want models to do the same. And the way this benchmark works is that it follows a violation of expectation paradigm, where 8 familiarization trials are followed by 1 test trial, and the model has to rate the test trial as plausible or implausible. So for example, the 8 habituation trials might show an agent repeatedly seeking out one of 2 objects, demonstrating a preference for one of them. And in a test trial, the agent either seeks out the same object or a different one, and the model has to judge which is suspected. And so to solve this benchmark, 2 major components are required. First, a way to model habituation, or the forming of expectations of a future behavior based on the familiarization trials. And second, a way to quantify how surprising or implausible the test trial is relative to those explanations. Our approach was to use a hierarchically Bayesian theory of mind, a model of rational agent behavior across multiple episodes that includes hierarchical priors and the efficiency and preferences of agents, as shown on the left of this graphical model. And this allows us to frame habituation as a form of hierarchical Bayesian inference. By observing the goals and actions of agents across trials, we can infer the agent's overall efficiency and preferences over time. And having made those inferences, the question then is how to account for surprise about a test trial. We do this by noting that surprise may correspond to several different belief dynamics. The first is surprise due to a sharp change in beliefs, and the second, surprise as inexplicability. In particular, given that we have a series of posterior distributions over goals and efficiencies for the test trial, we can quantify changes in those distributions or beliefs using a total variation metric and use it as a surprise metric. And then we can feed these belief change metrics into a product logistic classifier, along with the term that accounts for inexplicability, like how unexplainable the observations are as a whole under the model. And this gives us a plausibility classifier that balances different forms of plausibility or surprise. And adopting this approach, across the benchmark, we find that we achieve close to perfect accuracy across the board, outcompeting deep learning and imitation learning based methods. But not just that, I think in addition to achieving high quantitative performance, our approach also produces qualitatively interpretable inferences that help us understand how infants might be solving these tasks. So for example, I'm showing here a series of trials where the agent goes towards the cylinder during the familiarization trials. And over time, because we keep seeing it go towards the cylinder, the prior probability of the cylinder being the goal at the start of each trial increases. And then in a test trial, the agent goes towards the block instead of the cylinder, and this leads to a sharp change in inferred goal posterior, causing surprise. And that's all for this short 3-minute lightning talk. I'd like to thank some of my co-authors on this project and hope to see people at the poster presentation session later. Thanks.
Thank you, Sean. Okay. Next, we have Feng Gao presenting towards visual social navigation in photorealistic in indoor scenes. Please share your screen.
Yeah, can you hear me?
Yeah.
Okay. Hello, everyone. I'm Feng Gao from Tsinghua University. I'm glad to present our work on visual social navigation here. And I will present our work in 4
So we
parts.
cannot see your slides right now. Can you share again?
Oh, sorry. And can you see the slides?
Yeah.
Okay, thank you. Okay. Hello, everyone. I'm Feng Gao from Tsinghua University. I'm glad to present our work on visual social navigation. I will present our work in 4 parts. First, let me introduce what the visual social navigation is. VSN requires the robot to navigate among moving pedestrians with additional requirements of comfort, naturalness, and searchability. It's a fundamental ability for service robots, remains challenging when the states of pedestrians and high accuracy LiDAR are inaccessible. In this work, we address visual social navigation tasks via a reinforcement learning-based end-to-end model. In our work, the agent needs to make decisions upon visual observations and the goal compass. In reinforcement learning, the reward design is critical to form what we want the agent to be. So according to the task requirements, we divide the reward functions into 2 parts. For navigation, we follow the popular reward design in previous work, including the success reward, the decreased geodesic distance to the goal as a potential reward, and a slack penalty. For social compatibility, we punish the agent for dangerous collisions or getting too close to pedestrians. Then the total reward is the sum of these 2 parts. Since spatial perception is critical for the navigation task, we propose a goal-aware geometric mapping module before the visual encoder. For depth or semantic segmentation, we just project them from the front view to the top-down view via local mapping. For the goal compass, we draw it as the local map according to its coordinates. If it's out of the local map, we select the nearest point on the boundary to demonstrate its position. Then, in order to enable the agent to learn safe navigation without directly taking the true human states as inputs, we keep the actor of the policy still local and introduce a global view critic, thus establishing centralized training and distributed execution. That is a popular paradigm in multi-agent reinforcement learning. Furthermore, we propose an uncertainty-aware potential function method to balance multiple rewards. We use the global view critic to learn potential functions together with the original value function. We model the uncertainty as a Gaussian distribution with a learnable variance to achieve self-adaptive weight tuning. As the scale factor in social compatibility reward increases, the performance of the methods without UPF gradually decrease or even fail, while our method with UPF can achieve almost the same effect under different reward settings. To demonstrate the performance of our method, we compare ours with 2 representative baselines. We train and test these methods on the agility simulator and use some standard metrics for evaluation. The results show that our method can outperform both planning-based and learning-based baselines on agility scenes, with higher navigation performance and better social compatibility. We also conduct a ablation study to show the contributions of each part. Here we summarize our contributions, and due to the time limitation, I will just jump this slide, and you can find more details in our paper. Thanks for watching.
Thank you. Okay, so next we have Kirsten Herring presenting a human-centered approach to evaluating robot theory of mind.
Awesome. It's actually me presenting then, but I will share my screen and get started. Everybody see that all right? Awesome.
Yeah.
I can see it on the camera. Awesome. Perfect. Yeah. Hi, I'm here from the University of Denver, here to talk about our project, Do You Want to Build a Bot? And what we're trying to do with this project is address sort of three main problems in the social robotics field in general. The main thing is there's a gap in the understanding of whether humans will form a theory of mind of a robot when they look at that robot. And we want to be able to better test this and also then train machine learning models to help predict this in robotic designs, but we don't have the data we need to be able to do that, to train those models. And then if we then do get that data, we also need a way to validate those models and make sure that what they're spitting out and giving us is actually what is happening. And so to address those problems, we're developing an online platform to enable large-scale data collection, which I'll discuss a little more in a bit. We're also trying to then develop machine learning models for classification of existing robotic designs, as well as generation of new robotic designs using the data from our online platform. And then as a way to validate those models, we're working with neuroscience and FNIRS through studies to validate those models. Moving on to our platform, we are developing an online, as I said, research platform that allows users to build a robot design using basically 3D parts. And the reason we're doing it this way is because in existing and past research, the sort of common theme would be, we would design a robot as researchers and then ask users, okay, do you think this robot could feel hunger or some other thing that would be elicited by a theory of mind? But then the problem with that is, we have to have designed that robot, we have to have built that robot, then we have to reach out to users and get their feedback on it. We're trying to reverse that and say, okay, you design the robot for us, targeting this theory of mind attribute, is what we like to call it. But basically, we say to the user, design us a robot that you think could feel hunger or feel love, something like that. And then they can go in and use our platform and design that robot themselves exactly the way they want to. We're developing this in Unity and publishing it to our website, so it'll be easily accessible to everybody on the web. And then collecting data on that and collecting data on the robots and then using those for machine learning. Keeping this short, results to date, we're still relatively in the early stages of development and getting close to our sort of launch of the platform and starting our data collection on that. We've had some initial success with our platform prototype, but as well, we've also been looking into using graph machine learning. There's an example on the screen there for representing a given design that we get as a graph and being able to learn from that. With the different parts being different nodes in the graph and the interactions between those being important to how a user then perceives that robotic design. And I think probably just about out of time, so there's contact information. Love to discuss more with you guys at our poster. So thank you very much.
All right, thank you. Next paper is Bayesian theory of mind for false belief understanding human-robot interactions, presented by, I believe, Maddie Hilo.
Yeah, that's me. Yeah, I'm gonna share my screen. You all see the screen, right?
No, can you share again?
Okay, now I think it's okay.
Yeah, it's okay now. Yeah.
Yeah. Okay. So yeah, thank you for being here for my presentation about Bayesian theory of mind for false belief understanding in human-robot interactions. My name is Mehdi Ellou. I'm from the University of Manchester Cognitive Robotics Lab. And in the project I'm working on, we are interested about improving the behavior of social robots, because we know that social robots become more prevalent in our daily life. And it's important to have like social robots who can adapt their behavior to the user personality, preferences, and needs. And for that, we decided to use the notion of theory of mind in order to make the robot to input mental states of human in general. And for that, in order to evaluate the ability of theory of mind of social robot, we decided to use one of the measurement of false belief understanding in order to see if the social robot can infer when a person has the belief or contradict the reality. And for that, we introduce an experiment in order to assess the theory of mind ability for social robot to understand false belief in a helping task. And in order to permit the robot to understand when a person has a false belief, we use the Bayesian theory of mind, which is a well-known models, probabilistic models, who can permit to track the belief and preferences of a human agents, as you can see on the finger here. And more specifically for the experiment, we took the example from an original experiment from a psychological paper where we have different actors, different objects. And in the experiment, we have a true human, a searchers, and a triggers, and different objects, boxes, and a toy. And the social robot will play the role of the children's. And in the first step of the experiment, we have the searcher who try to put the toy in one of the boxes. And according to the belief condition that we set in the beginning of the experiment, it will either leave the room or stay in the rooms. In the next step, we will have the trigger who will switch to the location of the toy, while the searcher will watch the exchange or not regarding the belief condition. And at the final stage, we will have the searcher who will approach the box where it was originally located. And at this moment, we will try to analyze the responses of the robot to see if the robot will understand that the searcher has a false belief and will open the box where the toy is currently located, or if he knows that the searcher has a true belief and it will try to open the other boxes. And regarding that, so we simulate the experiment and we try to evaluate the prediction of the model regarding the desire of the human, which is if the human is interested in the toy or not, and also his belief. So if the human has a false belief regarding the location of the toy or a true belief. And as we can see for the desired of evaluations, we simulate how many times the agent will be interested in the toy or not. And as you can see for the desired evaluation, the model can have a real good prediction about the human behavior, more specifically about the human's preferences. It can even, when we set the rate to 0.5, which means that half of the time we will change human preferences to not interesting in toy and interesting in toy. And we can see that the models can predict well about that. The same goes for the belief about the human. We can, where the model can accurately predict when the human has a true belief regarding the location of the toy or false belief regarding the location of the toy, comparing to the different traits that we set about the belief condition. So now that we have the simulation, we can validate our models and the adaptability of our model in this kind of experiment. We can set up an actual experiment in real world situation in order to see how the people will perceive and how the people will interact and react with a robot who can understand false belief. And the next step also would be also to use the cognitive models for the Bayesian theory of mind to not only understand false belief social robot, but also to manipulate false belief in a different kind of scenario, cooperative or competitive. So thank you for your attention, and I'm glad to discuss later about this project.
All right, thank you. So we're going to have our last talk in the morning session. It's differences in brain activity during turn initiation in human-human and human-robot conversation, presented by Clarina. Can you share your screen?
Yes, sure. Can you see my presentation?
Yes.
Hi, everyone. My name is Ekaterina. I'm a PhD student at KTH Royal Institute of Technology in Stockholm, and I'm presenting the work that I've completed together with my collaborators in the first months of my PhD. The aim of my research is to apply insights from cognitive neuroscience to human-robot interaction to see how conversation with a social robot differs from talking to a human in terms of brain activity, and to find out whether brain data can become a valuable additional modality for autonomous user state evaluation by the robot using machine learning. In particular, I'm interested in conversational dynamics and how different is the communicative flow between human-human and human-robot interaction. And the focus of this study was turn initiation. That is how different is preparation for taking over a conversational turn depending on the conversational agent. For this analysis, we took an open source dataset of fMRI recordings of 3 conversations between the participants and 2 alternating agents, a human and a robot. And in their study, the authors divided the fMRI events based on the agent, taking for the contrast the whole 1-minute conversation. In our study, for our analysis, we used a novel set of events, dividing the conversation into short episodes. Studying free conversation using brain imaging has been quite limited until recently due to difficulties in data collection, which are caused by noise and motion artifacts. And therefore, our aim was to explore whether short events can be extracted from fMRI data of free conversations, and explore the neural correlates of turn initiation in human and robot dialogue. In our analysis, we defined 13 event classes in total, but for this paper, the events of interest were production, that is the time window of the participant speaking, comprehension, the time window of the agent speaking, and turn initiation, a 600 millisecond time window before the onset of the participant's utterance. And the duration of the turn initiation window was based on the psycholinguistics literature on picture naming tasks. And we took for contrast turn initiation with human agent versus turn initiation with the robot agent, and the reverse contrast. For robot versus human contrast, we did not find any significant activation. For the human versus robot contrast, we started at the whole brain level, at which the activation was not significant. And then we performed a small volume correction with search volume coordinates based on a previous study where this area showed activation in relation to a pragmatic task, and we found significant activation in this area. These results may suggest a deeper intention processing for the human agent in comparison to the robot agent during turn initiation. And we suggest that studying the turn-taking mechanism as a part of conversational dynamics can shed light on the differences in experience in interaction with a human and with a robot. And the aim of our future research is to collect new brain data of human-robot interaction to study the user's conversational experience, such as conversational engagement, and to see how can brain data be used for autonomous engagement detection using multimodal machine learning. And unfortunately, I will not be able to present at the poster session, but if you have any question related to this or my future work, please feel free to contact me by email, and thank you for your attention.
Okay, thank you. So this basically concludes our morning session. So thanks for all the